Hello, class. Okay, so now we are starting chapter 4, actually, and this chapter is really all about two new kinds of functions I'm going to introduce. Okay, but if you notice something weird is actually I have decided to combine sections 4.1 and 4.2. Okay, because I kind of just hate how your book does it. Okay, so both of these sections are about what we call the exponential function. Okay. Function. Okay, and the exponential function looks like this. Okay, so we have f of x equals a to the x. Okay, so it's not x squared. Right here, the number was on top and the x is the base. Right, this is the opposite, where we have the base is a number and x, the variable, is actually the power. Okay. So because this could get a little complicated, we like to force a to be a positive number and also not 1. Okay. And so this function has a domain, negative infinity to infinity. So it's like polynomials. Okay, it's nice. But its range is 0 to infinity. Okay. All right, so let me start with a graph. Okay. So for example, I'm going to have this function, 2x. All right. And I'm just going to, plug in some stuff. Okay, so first of all, I want to find out its y-intercept, which is 1. Okay. And then I'm going to plug in 2, and what happens? I get 2 squared, which is 4. Now I'm going to plug in, oh, why didn't I plug in 1? F of 1 is 2. F of 3, 2 to the power 3, 8. F of 4, 2 to the power 4, 16. Right? But remember, right, the domain is everything. So I can plug in negative numbers. So what happens when I try that? So what's negative 1? Right? That's 2 to power negative 1, which you should remember from way back in like chapter 1 even, that if a negative is in the power slot, that means you just flip it across the denominator. So f of negative 1 is a half. F of negative 2 is 1/4. F of negative 4 is 1 over 16. And so if I plug all of those into, if I make all of those dots, we see that I get something that looks like this. Okay. And actually, right, like if I check end behavior, right, we see that I get 0. So actually, this function, kind of like the rationals, this function has a horizontal asymptote at y equals 0 by default. Okay. All right. So this is what it typically always looks like. Okay, so a to the x looks like this. Okay. Now we can combine this new graph with what we learned from chapter 2. And so if I ask you to graph something that looks like this, you should be able to just do it automatically, right? You should be like, oh, this means go down 2. This means go left 1. This means reflection. So this is what 3x looks like, 3 to power x. This is what happens when I reflect it. Now I'm going to move it left 1 over down 2. Okay, so down 2 means that the horizontal asymptote also moved down 2. Okay, and then left 1 just means I go left 1. Okay, so something like this. All right, so ta-da. Okay. Now, something weird can happen, okay? So recall the example, all right, 5 to the negative x, right? Well, because we know power rules, right? We know that this is 5 to the negative 1 times x, which I can just do this, okay? So a negative power really means a fraction, okay? And so if you see if a here is a number that's smaller than 1, that actually means you get a reflection, okay? So this will look like that, okay? Across y-axis. Okay, so even though this doesn't have a minus sign here, it secretly does because it's 5 to the negative x, okay? So if you see fractions in the exponential, remember to, either check the end behavior, okay, or know that it's a reflection across the y-axis. All right. Okay, so now, just to kind of fast forward something, the main point of both of these sections for us is going to be compound interest. Okay, so we're going to learn how to calculate compound interest. So I'm going to have this formula, okay, which is very important. All right, so this is crucial, okay, very much required. You must memorize this, okay? And let me explain the parts, okay? So, if we remember the simple interest formula, pretty much everything's kind of the same. So P still means principal, okay? R still means interest rate. T, as always, means time. Okay, so you just need to figure out what's N. And N is the special part, right? So N is what I'm going to call the number of times you compound in a year, which is kind of complicated, and we will explain. Okay, and then A is what you're looking for. So A is the amount, like the total amount you get after. Okay, so N. Okay, so all of these interest problems are word problems. And so you're going to need to be able to decipher the word problems to get the N. Okay, so if they say you compound annually, that means N is 1 because you compound once a year. Okay, now this one is rare, but if you compound biannually, okay, that means N is 2. Okay, this is also called semi-annually. You probably won't get questions like that. Okay, one of the most common is quarterly. Okay, so if they say you compound quarterly, that means you compound once every quarter, which means you compound 4 times in a year. Okay, and then, right, if you have like a bank account or anything that pays interest, monthly means 12 because there's 12 months in a year. Okay, and now here's the one you might not know depending on how much of an adult you are. All right, weekly, okay, means N is 52. All right, now I didn't know that when I was, a normal person. All right, what I want to say is N is 52 and you should just memorize that, because what I do not want you to do is be like weekly. Okay, so how many weeks are in a year? Okay, well, there's 4 weeks in a month and 12 months in a year, so I'm going to do 4 times 12, and get 48. So there's 48 weeks in a year. Okay? No, that's just wrong. Okay? If you count, it's actually 52, approximately. Okay? So weekly is 52. Daily, just always assume it's not a leap year. Okay, so 365. All right. And then if they say seconds, then that means n is 31,500,000. 31,536,000. There's definitely a song about this. 31,500, 600 minutes. That's minutes. Okay. All right. And then if they do any more, then that's crazy. Okay. But let's do a problem. So you decide to invest $1,000. All right. Principal. When you're 18 at 7% interest rate. Compounding quarterly. How much money will you have when you retire? At 65. Okay, so this is the hypothetical situation where you invested just $1,000 right when you hit 18 and then did nothing else until you hit 65. Okay, so the first thing is you need to like read the problem, right? And I already kind of started doing that for you. So you invest $1,000 when you're 18. Okay, so 1,000 is P. 7%. Okay, so we know what R is. Compounding, they said the word quarterly, so you know what N is. And then these ages is what's going to tell us the time. Okay, so we need to figure out the time actually, right? So how long is this going to be invested? Well, it's going to be 65 minus 18. So 47 years. Okay. So we're investing this for 47 years. Okay. R is going to be 7%. But remember, we can't plug in percents into our formulas. So this is going to be 0.07. Okay. P is just 1,000. N is quarterly. So that means N is 4. So then I just plug all of these into a calculator. Okay. And also, okay, so chapter 4 is definitely the chapter where you can use a calculator because these numbers will be bad. Okay. So, and you're just seeing that right now, right? So here I plug in all of the info into my formula. And, you know, now I need to just figure out what it is. Okay. So $1,000. The inside chunk, if you punch it in a calculator, will be approximately this. Or not, it'll be exactly that, my bad. The top is going to be 188. So then if you punch that into a calculator, you're going to get 26,089.7888 forever, which is going to be approximately $26,000, $26,089.79. Okay. So if any of you are 18 and have $1,000 to invest, it's recommended. Unless you don't want $26,000 in, 47 years. Okay. But so this is basically how all of the word problems will go. Okay. They're all just gonna be like, here's an investment for blank amount of years, compounded quarterly, annually, biannually, and you just plug into the formula. Okay. Now, I'm gonna do something a little strange. Okay. So my next example is going to be a little interesting, okay? So I'm going to invest $1 for 1 year at, okay, 100% interest rate. And what I'm gonna change is how much I compound, okay? Because I kind of want to show you the power of compounding, okay? So when I invest this into something that compounds annually, okay, 1 times 1. So if I plug all of the numbers in, 1, okay, you get 2, okay, which that's actually simple, right? So if I invest $1 for 1 year at 100%, and it only compounds once, that means by the end of the year I have $2, okay, which is not exciting. But what if I compound twice a year? Okay, so that means I actually, when I plug in, I'm gonna get this, okay, which is 1.5 squared, which is $2.25. So an extra quarter happens when I compound just one more time that year. Well, what happens if I compound quarterly? Well, if I compound quarterly, I get this thing, which gets me approximately $2.44. Okay. So let's kick it up a notch. Let's compound weekly. Okay, so right now it's getting a little big, right? 52. So this is $2.69, it is 69 cents, okay? And so something you should be noticing, right? Like I went from $2 to 2.25 to 2.44 to 2.69, right? And 52 is way bigger than 4. All right, so then let me just go out of hand here. Let me do it daily, right? So 365. This actually gets you 2.71, right? So it's going up, but it's going up really slow, right? So let me do it every second, right? Which is this number. Okay. So if I do it with 31,536,000, 31,536,000, I actually get $2.71. So actually, if I take this expression, right, which this is the interest formula that I've kind of been doing, the weird one. If I take n to go to infinity, right, if I compound infinity many times per year, this thing goes to e, which is a number, which is approximately 2.71. And I think it's an 8 here, but it's like pi. Okay, e is like the numbers that is irrational and goes on forever. Okay. 1. Okay, so actually, this is what section 4.2 technically, but it's the same thing. We have this function, e to the x, okay? And e to the x is like the exponential function. All right. So when someone talks about exponential functions, they really mean this one. All right. They don't really mean these with like the number 5 or 3 or 2. Okay. They actually mean this one with the e. Okay. And so, really all we know about it, all that's easy, is that you know the y-intercept is 1. Because anything to the 0 power is 1. Okay? Besides that, you don't really know anything about e. Okay, so your graph should look like this. Okay. So, again, I'm just going to do one example, right? If you have negative e to the x plus 2, e to the x, negative e to the x, plus 2, so the horizontal asymptote goes up 2. Okay? All right, so you should be, it should look better. You should probably label, but right, you should be able to do everything you already know how to do, just with this base knowledge, okay, of just this is what e to the x looks like, okay? Now, e to the x lets us do something special with the interest formula, okay? So now I can introduce the continuously compounding interest formula, okay? And if you are like, no one ever, like, what is this? All right, you are unaware of that people will do anything for money, all right? Because we are literally harnessing the power of infinity to make like an extra, like, I don't know, like an extra 2 cents. All right. So, right, we have the amount, we have the principal, we have the R is the rate, T is the time, and E is E, right? E is E, which is a number, which is a button on your calculator. So if you're using a scientific calculator, you should have a button that literally just looks like the letter E. And that's what this one is, okay? So how do you know when to use which formula, okay? The answer is this formula needs this word, okay? When you see the word continuously, that's when you know that you need this formula, okay? Whereas when you see any of these, okay, I didn't say this was seconds. Okay, yeah, when you see any of those words, that's when you know it's regular compound interest, okay? But let's do the same example, okay? So let's also invest $1,000 when you're 18 until you're 65, okay? At 7% interest rate. All right, but now we're gonna compound continuously. All right, what happens? So now we're going to use this formula. So 1,000 e to the 0.07 times 47. Okay. And remember, it's 47 because that's how long we're waiting. Okay. Well, this one, you actually just need a calculator. So like, not only is it not recommended, now you just need it. Okay. And you're going to get $26,842.86. So after you plug this in. So now if we compare, right, this is 26,850-ish. And we go up to the old example, this is 26 and 89. So literally, that's like an extra $800 if you compound continuously as compared to compounding quarterly, okay? So the power of compounding is magical, all right? Some people call it the 9th wonder of the world, okay? But that's kind of it for this section, all right? We're gonna do a lot more with exponentials, But what you need to know from section 4.1 and 4.2 is just, this is the compound rate interest formula. This is the continuously compound rate interest formula, okay? And know how to, plug into them. And I highly advise for the study guide, right, for the test, that you actually practice punching this into a calculator, okay? Because you're gonna need to put like parentheses in the right spot. All right, when I teach this in person, I have like many students that ask me to help them punch it into a calculator. So I would say definitely practice getting the correct numbers, okay? But that's really it for section 4.1 and 4.2. All right, see you guys next class.